So before we talk about angular momentum, I want to remind you of a couple of things about linear momentum. So recall linear momentum, we used p for the symbol. It was equal to the mass times the velocity. It's a vector. If you have a whole bunch of objects in a system, you can find the momentum of the system by adding up as vectors the momentum of each object in the system. So the momentum of the first object plus the momentum of the second object plus the momentum of the third object, so forth and so on. And we also had that the net force on a system or on an object, that was equal to the change in the momentum. So if you ended up having no net force, that is, the net force was equal to 0, then momentum was conserved. So this was of course also true for the individual components. So if your x component of the net force was 0, then your x component of momentum was conserved. And if your y component of the net force was 0, then your y component of momentum is conserved. So you could do collision problems looking at the momentum. So here, let's just do x is horizontal and y is vertical. We'll have a little skateboard. It'll be traveling along at a speed. Let's just make it 2 meters per second. It'll have a mass, let's call it 1 kilogram. Then if we drop a blob of clay right on it, let's say that blob of clay has a mass of 0.5 kilograms, then there'll be a collision between the clay and the skateboard. And then after the collision, you'll have the skateboard with the clay stuck on it. And this new combined object will have a bigger mass. It'll be the 1 kilogram plus the ½ kilogram from the clay, or 1.5 kilograms in total. And it'll have a new velocity, which we don't know yet. But we had the velocity before and the velocity afterwards. And looking at this, we can see there is no net force in the x direction. Because it's traveling along, the only forces we've got are like the normal force from the ground on the skateboard, and then the gravity force on both the skateboard and this blob of clay, but those are all vertical. Horizontally, we don't have anything. So the x component of momentum is conserved. So we can say, all right, looking at the momentum, the x piece before the collision, it has to be the x piece of the momentum after the collision. And the x piece of the momentum before the collision, well, it's going to be the x piece of each individual component, each individual object. So for the skateboard, that'll be the mass of the skateboard, that 1 kilogram, times its x velocity, which is all of its velocity, the 2 meters per second, plus the mass of the blob of clay times its x velocity, which is 0 because it's only traveling in y. And that has to be the x component of the momentum afterwards. So it'll be the mass of the total object times the velocity of the total object afterwards. All right, so that's 0 because we're multiplying by 0. And we have 2 kilograms meters per second equals 0.5 kilograms times this unknown velocity. We divide by 1.5 kilograms on both sides, cancels here, kilograms cancels there, and we get out 4.3 meters per second, or 1.3, or far over 3, or 1.3 meters per second, for our velocity afterwards. And it's less than the velocity of just the skateboard before, and that makes sense because now we've got more mass, so we've got less speed. All right, so that's linear momentum. For angular momentum, we're going to use the symbol L, and it'll be either a big capital L or a lowercase l, and I'll write them both as scripts just so it's really clear they're L. And there are two ways to find it. The first one, we'll use the lowercase l. The angular momentum is given by the moment arm times, or cross product with the linear momentum. So this is a lot like, going from torque and force. That's the connection there. So, recall when we wanted torque, we could get it from force like that. We're doing a similar thing to get the angular momentum. But we can also get the angular momentum, and here I'll use the big uppercase L, by multiplying the moment of inertia times the angular velocity. And that's really similar to our linear momentum definition. It's the inertia term, mass and linear, moment of inertia and angular, velocity and linear, and angular velocity when you're in angular world. So similar things. And just as we could add up the linear momentum of a system by adding up all the individual linear momentums of each object, we can do the same thing with angular momentum. And that's why we have these two different symbols. The capital L, which is usually what we use for a system or a big complex object, and that's equal to the sum of all of the angular momentums of the object's components. So the first thing in the object, or the system, plus the second thing, plus the third thing, and so forth and so on until we've added them all up. And just as we had with linear momentum, we've got with angular momentum the sum of all of the torques acting on an object, or the net torque, is equal to the change in the angular momentum. So just as we did for linear momentum with no net force, meaning there was a conservation of linear momentum, if there's no net torque, if the net torque is equal to 0, then the angular momentum is conserved. So just as we did over here with linear momentum, and we had a collision, and we could use the fact that if there's no net force, the momentum's conserved, we can have a collision over here and use the fact that there's no net torque, the angular momentum is conserved, to find the velocity here, and we can do the same thing here. So as an example, say we've got a disk. There it is. It's got an axis of rotation like this. So it's pinned in place, so it can only rotate around like this. And if it's going this way, if it's turning that way, I guess that means it has an angular velocity pointed up along its axis of rotation, like that. And what do we know about this? Well, say it has a moment of inertia of 3 kilograms meters squared. It has an angular speed of maybe 4 radians per second. And now we're going to drop a blob of clay again onto it. And let's just make this blob of clay have a mass of 1 kilogram. And of course, because now we're rotating and we care about moment of inertia, we have to know exactly where we drop that blob of clay. We're going to drop it on the edge of the disk. So we'll put it on the outside radius. That'll be 0.5 meters. So the radius of the disk is 0.5 meters, and that's where we're dropping this blob of clay. There will be a collision, smash, and then later on we're going to have this blob of clay on our disk. It's still held in place by this axis of rotation, this pole or whatever it is that's holding it here. So it can only rotate like this, and it'll still be going in the same direction, though it'll have a different speed. This was before the collision. After the collision, it'll have a different speed. And when this drops, it'll exert a force here, and there will be a torque because that force is over here, far away from the axis of rotation, but it would try to make the disk rotate like this, so sort of flip. So here I've got my handy disk. Say it was rotating like this, If I drop the mass here, it wouldn't want to make the disk rotate like this, it would want to make it flip like this. And this rod that's holding that's preventing that from happening. So there would be a torque from the mass of the clay trying to turn it this way, but the rod would be creating a counter torque. And those two would cancel. So here there's no net torque. So angular momentum is conserved. Okay, so that means the angular momentum before the collision equals the angular momentum after the collision. Before the collision, we have the moment of inertia of the disk. It's rotating, and its angular velocity. The mass isn't rotating, and we don't have to worry about it. It's not rotating about this axis. So it doesn't have any angular momentum. And then after the collision, well, we have a new moment of inertia. It'll be the disk, that I that we're using, plus the mass that we dropped times the square of where it is, and we can pretend it's a point mass because it's all sort of squished in right here. So there'll be m, it's a mass r, the whole thing has moment I guess we can put a d on that because it's just for the disk, and it'll have a new angular velocity, and we can solve for that. The angular velocity will be equal to the moment of inertia of the disk, which is the old moment of inertia, over the new moment of inertia, which is the disk plus that mass of clay, times the angular speed before the collision. All right, now we can plug in our numbers. So 3 kilograms meters squared over here, shouldn't be cubed, it's squared. And then 3 kilograms meters squared here, that's for I. Plus the mass, it's 1 kilogram, times the distance where that mass is, 0.5 meters, that'll all be squared, times the old speed, 4 radians per second, and all of that will be equal to the new speed. All right, and if we go through and do the math, what do we get out? Now this will just keep the 4 radians per second for now, but this guy will be 3 kilograms meters squared over 3 plus, all right, 1 and 0.5 squared, so that'll be 0.25 times 1, 0.25, so this will be 3.25. The units will be kilograms meters squared, good. So kilograms meters squared, those units will cancel out. We'll have 3 over 3.25 times 4. Plugging that into our calculator, we'll get 3.69, and the units will be radians per second. And that'll be our new speed. And you see again, it's smaller than the old speed, it's going more slowly, but that's because the moment of inertia is bigger than it used to be. So in order for the moment or the angular momentum to be conserved, if the moment of inertia goes up, the speed's got to go down, and that's what we see. So that's how you deal with angular momentum, both what it is and then how you can use it to help you solve what's going on in a collision problem.